Hello, everyone, and welcome to today's webinar. My name is Sahar Paksat. I'm the Marketing and Communications Coordinator at Klohn Crippen Berger. Welcome to our second webinar presentation of this year. We're glad to have you join us. In today's webinar, we will go through a study commissioned by the Mine Environment Neutral Drainage Program, or MEND, to examine and compare alternatives to conventional tailings management. Before we begin, I'd like to cover a few housekeeping items. On your screen, you should see several items, such as the slides, the speaker bios, and the Q&A box. All of these are resizable and movable, so feel free to move them around to get the most out of your desktop space. If you have any questions during the webinar, you can submit them through the Q&A box. A copy of today's presentation is available to download from the resource list, which you can access at the bottom of your screen. If you come across any technical issues, just click on the Help or the question mark button at the bottom of your screen. Lastly, an on-demand recording of this webinar will be available and can be accessed using the same audience link that was sent to you earlier. You will get an email about it as well after the webinar. So today's presenters are Kate Patterson and Lindsay Robertson. Kate is a water resources and tailings engineer and an associate in our Vancouver office. She has over 10 years experience in mine environment, tailings management, and water resource projects throughout Canada and internationally, including on some of the largest mining operations in the world. She currently manages multidisciplinary design teams for large tailings dams. Lindsay is a geoscientist and an associate based in our Sudbury office, where she leads the Ontario Environmental Group. She has 15 years experience with the assessment of environmental impacts from mining, and she specializes in geochemistry and environmental soil sciences. She has a technical focus on the integration of geochemistry with tailings management and closure. Over to you, Kate.
Thank you, Sahar. As Sahar said, we will be presenting the study KCB conducted on tailings management technologies commissioned by the MEND project here in Canada and funded by the Mining Association of Canada. This study was initiated in 2015 after the 2014 Mount Polley tailings dam failure and the subsequent Technical Review Board report and recommendations. Since this report, there has been a renewed interest in dewatering technologies and their corresponding tailings facilities. This study was initiated to review the applicability of dewatering technologies for Canada and their ability to manage physical and geochemical risks. The research and information collected and presented in this study was conducted over 2015 and 2016, with the final report being issued in 2017. Lindsay and I would like to extend special acknowledgement to the core team that drove this study. Co-authors include Harvey McLeod and Bob Chambers. We were also supported by a large team at KCB and the support team from MEND and MAC. We would also like to extend thanks to the mining companies who shared their information and lessons learned, and the many reviewers of the report. Thank you. The report summarizing the study can be found online. The link will be provided later. This presentation will hit the highlights of the study. First, we will introduce the study, the objectives, and the methodology. Then we will outline our framework for how we've looked at tailings management strategy. Then we will present some case studies that provide lessons learned, and we will conclude with our conclusions and path forward. Study objectives was to identify the state of practice of tailings dewatering technologies and their associated facilities within Canada. Once we identified that, we were going to assess the strengths, limitations, and physical and geochemical risks across the life cycle of those tailings facilities for the technologies and compare them to conventional slurry. Then we identified the knowledge gaps and made recommendations for future work. As with all high-level studies, we have a long list of disclaimers. which really just boils down to conclusions are generalized. Undoubtedly, there will be exceptions, and the scope of the study does not cover everything, in particular dam design and closure design and their related tailings dewatering. And we also are focusing on surface tailings facilities and not underground disposal of tailings. The study methodology took 3 main steps. First, we are looking for the current state of practice in Canada, and we did that through literature search, database search, and a questionnaire to all Canadian mines. Then we looked at comparing the dewatering technologies and facility types and how they compared to conventional tailings management. And this third step was to identify lessons learned and knowledge gaps. No one-size-fits-all tailings technology for tailings management. Although this slide appears comical, it is an important concept from our study. Tailings management boils down to risk management and should be focused for the life cycle of the facility, especially post-closure. Tailings management strategy should be risk-based. Therefore, the tailings technology that is selected should consider the risk profile of all alternatives and implement the strategy that best manages all risks. Our presentation objective today is really to give you a brief overview of the study and present our key learnings through the case histories.
Now we're going to get into some of the details of the tailings management strategy considerations and what we uncovered during this study. We looked at tailings management strategies from 4 different perspectives: the tailings characteristics, the site conditions, the available technologies and facility types, and the social and regulatory environment. But for this presentation, we're going to focus on 3 key areas: the tailings characteristics and scale, available technology and facility types, and the site conditions, which will encompass to some degree the social and regulatory environment of your site location. You want to be somewhere in the middle of this Venn diagram. And your goal, as Kate mentioned, should be to minimize the short-term and long-term risks of the facility. All the key aspects should be evaluated. Tailings characteristics, including both physical and chemical characteristics, what is available to you in your region, as well as the site conditions that you're dealing with, and presumably the objective that you're working towards for the tailings technology. When we start characteristics and scale, we're going to talk a little bit about physical properties, so the grain size, the rheology and plasticity of the tailings, the chemical properties of both the solids and the water that you're containing in the tailings facility, and your mill production rate and anticipated throughput. Because as you'll see later in our presentation, not all available technologies are scalable. Now I'm going to talk about physical tailings properties. What you're seeing on the slide here is the ICOL 2017 classification system for tailings, and this is what we applied throughout the tailings technology study. The tailings are classified according to their particle size distribution and Atterberg limits. And you'll see here we have several tailings types, ranging from coarse tailings to hard rock, altered rock, fine, and ultrafine tailings. Now, iron and base metal tailings are typically characteristic of the coarse and hard rock tailings ranges. When we get into gold and polymetallic deposits, you can sometimes see them crossing the altered rock and fine tailings boundaries. When we talk about our case studies later, we'll get into some of the details for those specific studies and their tailings properties. Kate's going to discuss tailings properties later on in the presentation as it relates to application to technology types. But here I want to emphasize the importance of tailings characteristics and classification prior to tailings technology selection. We're using this classification system for particle size and Atterberg limits, including the fines content of the tailings, the plasticity index, and the liquid limit to help understand whether or not your tailings are appropriate for different technologies. When we consider the chemical properties of the tailings, I'm going to point you to the reference from the GUARD Guide. So this was developed by INAP in 2009, and it's a general classification and characterization program for the metal leaching and acid rock drainage properties of tailings and other geologic materials. The tailings type in the MEND study have been simplified to classify these tailings based on management strategies and potential water quality outcomes. So here we've classified the tailings based on their potential to generate acidity from sulfide oxidation processes. And this is important when considering short and long-term management strategies for tailings and sulfide oxidation. This will help you understand whether or not you need to limit oxygen or water to your tailings pile during operations and closure, or perhaps both. The next category is sulfidic processes that generate metal leaching. And so this is what we typically classify as neutral metal leaching, where we may not have acidity produced from the tailings, but we do have metals being liberated based on oxidation processes again. The third classification in the study report is non-sulfidic leaching. So this is leaching processes that are not a result of sulfide oxidation and often include dissolution processes that occur. These types of tailings tend to need to be managed in consideration of water being contacted and not necessarily oxygen ingress into your tailings. Then we have low reactivity tailings. Now these is the rare tailings type in the industry. However, there are several projects where the tailings do not produce significant levels of metals or acidity. When we're talking about tailings characteristic, is obviously your tailings supernatant in quality. So what process reagents are you using, and how does that need to factor into your tailings water management? What treatment is needed for this site? What is your tailings settling time going to look like? What's the mill production rate? How scalable is the technology? And how effective is this technology overall for your type of material?
Next, we're going to talk about the available technologies and facility types that we looked at. Our framework for classifying dewatered technologies and facilities. They are presented on this graph. Along the bottom, we have different states of dewatering technologies. So this represents tailings from unthickened, thickened, high-density thickened, paste, and filtered. And the difference between these is really the solids content by weight. So that is how much water has been removed from the initial slurry. So as you can see, unthickened acts like a water, and as you move forward, you take out more and more water, and then the tailings act like a solid. Along the y-axis of the graph is yield strength, or stress. Yield strength or stress is defined as the amount of force required to make a fluid flow. So as you can see, the percent solids content along the bottom is related to the yield strength it has, hence the name paste. It acts like a paste. Along the top, we have our facility types, which Lindsay will go into a little bit further. We have conventional, where you are storing typically unthickened or thickened tailings. We have a thickened or paste type facility, where you would store high-density thickened or paste tailings, and then a filtered facility, or pile, where we would store filtered tailings. The difference between these we will go through as we introduce each of the facility types, but they all will always differ in process, transportation, deposition, and how the tailings act within the facility.
Starting out with a conventional facility, this is obviously the most popular tailings facility type within Canada. It's what we've been using historically. There's a lot of advantages to a conventional tailings facility and tailings dam construction. For instance, the ability to use tailings in construction or cyclone tailing sands for dam construction. These facilities often have large ponds within the facility itself to help with water storage and water reclaim, as well as storm attenuation. And it's the type of facility that we're most familiar with. Now, most of the water management here occurs behind the tailings dam itself, which is one of the key risk items that was discussed as part of the initiation of this study. If we want to manage our water more effectively behind the tailings dam, the conventional facility doesn't necessarily allow us to decrease the water volume stored. One of the benefits to this facility type, however, is that we can progressively reclaim off in the downstream slopes, and we have a sufficient amount of water being able to be returned to the mill. There's also a lot of benefits to long-term closure when we talk about chemical stability, and sulfidic metal leaching and acid rock drainage, where a water cover in the long term can help with closure water quality management. There are some challenges with conventional tailings facilities, which is why we evaluate the thickened and paste facility type as part of this assessment. Now you'll notice the biggest difference with the thickened and paste facility is the majority of water is managed outside of the tailings dam. Now this doesn't necessarily minimize the amount of water that needs to be stored in the facility or managed as part of the tailings. It just changes the location that this water is managed. Now this is seen to be beneficial when we talk about risk management in tailings because we're not looking at a potentially large volume of tailings being released during a dam break scenario. One of the challenges, though, with thickened and paste facilities is they tend to take up a larger surface area depending on the overall design. And some of the paste facilities that we reviewed did have a larger surface area, and so we actually had a lot more water that needed to be managed because of the catchment size. Another challenge with this thickened paste approach is that typically it can be challenging to achieve the appropriate tailings properties for the facility type to be effective. And people typically get about 5% less in their tailings densities than what is designed for. In this facility type, you may require positive displacement pumps for transportation, which can add to logistical challenges and costs for the facility overall. These facilities typically, especially when we're talking about a paste cone, cannot be progressively reclaimed, and so we're looking at closure after the fact. When we look at a similar configuration set up for the filtered facility, you'll see again that the majority of water storage occurs outside of the tailings pile itself. Now the best practice with a filtered tailings pile is to have a structural zone on the outside that acts like a dam. For the filtered tailings pile, there's generally low seepage rates, with seepage coming from infiltration and not a standing pond. There will be some runoff from the facility that will generally need to be managed as contact water, of course depending on the geochemical characteristics of the pile. With the external water storage, the pond will need to be sized to manage not only your storm events or contact water runoff from the facility, but also enough water to handle your water reclaim for the mill circuit. Now with a filtered tailings pile, you can have progressive rehabilitation and control over the surface configuration, which can be helpful. These as well can have a much smaller footprint than a conventional tailings facility or a high-density thickened or paste facility. However, that is entirely dependent on the design of the facility itself. There tends to be a low phreatic surface in the tailings pile, which again is beneficial for water management, but may not be beneficial for geochemical management. Long-term closure of filtered tailings facilities isn't well documented yet, and so the management of geochemical processes and effluent in the long term or closure of these facilities has yet to be developed in detail.
Next, I will briefly touch on the relationship between tailings properties and available technologies, facility types, and some considerations. Depending on the objectives of your tailings management strategy and facility type, there will be design targets for dewatering equipment. For example, the design of a high-density or paste facility may require that tailings be dewatered to a solids content such that the tailings release little to no water upon deposition, exhibit non-segregating behavior, have a low hydraulic conductivity and high moisture content, and deposit in steeper slopes. However, to achieve these tailings properties, the tailings need to be dewatered to a high enough solids content, referred to as a design target. Case studies have shown that oftentimes mines can struggle to get their equipment to ramp up to the design targets in a timely manner if they achieve them at all. Also, even if the solids content design target is achieved, the properties of the tailings have been overestimated, for example, the tailings deposition slopes. Typically, high-density thickened tailings deposition slopes are steep for a short distance, then flatten out to similar slopes as unthickened tailings. Similar with filtered tailings, as Lindsay mentioned, it is good practice to include a structural zone in a filtered tailings facility. The structural zone should be dilatant. In order to achieve dilatancy, the tailings need to be compacted close to the optimum moisture content. Therefore, the moisture content design target for filtering would need to be close to the optimum moisture content, which can be quite low for certain types of tailings. How easy is it to dewater tailings? Well, that depends on the property of the tailings. As you can see here, this is our physical classification of the tailings on our yield stress and solids content graph. This shows us that the coarser the tailings with less fines content, it is easy to dewater those tailings. The finer the tailings, for example, the ultra-fine tailings types, like a mature fine tailings from the oil sands, those can be very, very difficult to dewater to high solids content before you have high yield stress. With high yield stress becomes limitations with the equipment and transportation.
Next, we're going to talk about how the tailings characteristics and scale of the facility fit in with the site conditions. And we're going to do this by looking at a relationship between the climate and production scale of existing facility types in Canada and worldwide. When we look at conventional tailings facilities, and this is where we're talking about a typical percent solids ranging from 20 to 40%, we see that these types of facilities span a very broad spectrum of climate, going on the y-axis from a net negative water balance, minus 3,000 millimeters, to a net positive water balance of plus 2,000 millimeters per year. And a tailings production rate from as low as 500 to 1,000 tons per day up to approximately 175,000 tons per day. So conventional tailings have been broadly applied in Canada and internationally, and I will note that these dots here represent all projects studied, not just the Canadian projects. So when we compare this to our tailings technologies to look at things like thickened tailings, you can see from this graph, with the y and the x-axis remaining the same, where we have tailings solids ranging from 40% to 60%, we still have quite a broad spectrum of tailings facility types applied. But you'll notice just a slight decrease in the overall net positive water balance. And this is due to the fact that thickened tailings is often driven by a need for an adjustment in water management or water reclaim for the facility. So here we see this more applied on the lower end of the climate scale, where we tend to have more evaporation than precipitation. When we take it one look at paste and high-density thickened tailings, now admittedly there were not a large number of projects evaluated for this tailings technology type. We have tailings solids ranging from approximately 60 to 75%. And we see that it's generally in that low tonnage per day range, but again ranging from a net negative to a net positive water balance. And I will note here, in this circle, there is one high tonnage rate, high density thickened project on the go in Chile. So it is being extrapolated and applied at higher production rates, and we're waiting to see how successfully that's implemented. Filtered tailings, where we see a percent solids generally greater than 75%, most of the projects evaluated had a lower ton per day, generally below 40,000 tons per day, and are clustered across the spectrum of net negative to net positive water balances. So we see here a general trend across climate and production scale where these dewatered technologies are more applied at lower tonnages. However, we are seeing that being extrapolated now towards higher tonnages.
We are now going to jump into some of the case histories and provide some lessons learned for those. The information for the case history database was collected through a variety of ways. First, we sent a questionnaire to over 260 mining companies requesting information on their tailings management strategies and tailings properties. We had 36 replies. We then supplemented this with looking in the KCB's library and previous project files. We also did a literature search conducted by KCB's professional librarian. We also contacted mining companies directly if we needed further information, and our mining companies' clients. We also looked at the associations we're a part of, including the International Commission on Large Dams, the Mining Association of Canada, and the Canadian Dam Association. And of course, we contacted the provincial, territorial, and federal government agencies to make sure that we identified all the projects that we could. Now these are the projects in Canada that use dewatering technologies as of 2016. As you can see, there's not very many of them, but more and more projects are considering them. They're in the study phase and are considering implementing dewater technologies. The point is technologies are improving, designs are improving, and operations and maintenance of these are becoming easier. The results of our review are presented in this table. On the left-hand side, we have the count of dewatering technologies implemented across Canada. And on the right-hand side, we have the different facility types implemented across Canada. Specifically for the PACE facility types, one project is in care and maintenance and was used to increase the capacity of an existing conventional tailings facility. So the 3 high-density thickened PACE tailings include one that is actually a conventional tailings facility. As well for the filtered facility types, we have one in care and maintenance, one in construction. Overall, based on these numbers, about 10% of mines in Canada are implementing dewatered technologies.
We're going to dig into some details on some of these facilities that have implemented dewatering technologies, why they've done it, and what the benefit and challenges have been. And we're going to start here with Canadian Malartic. So this is a conventional tailings facility that has implemented thickened tailings at about a production rate of approximately 55,000 tons per day. Malartic Tailings Facility is located in Val-d'Or, Quebec, and it's an open-pit gold mine. We have a 64 to 65% solids deposited in this conventional facility. The climate here is a net positive water balance and does experience snow cover in the winter. This mine has been operating since 2011. Canadian Malartic is generally done outside the facility. The supernatant runoff water reports to the reclaim pond located to the southeast of the facility. There's an internal overflow spillway situated near the center of the south perimeter and central perimeter dikes. The supernatant and runoff is 100% recycled to their process plant. The Tailings Canadian Malartic mine are along the boundary between hard and altered rock tailings. Cyanide is used in the process here, and according to the classification scheme and Directive 019, a significant proportion of the ore, waste rock, and tailings are potentially acid generating or leachable. So these would be along the sulfidic, metal leaching, and acid rock generating scale of our tailings properties. So why did Canadian Malartic decide to go with a thickened tailings technology? The primary driver was dam safety and limiting water storage on the site. The thickened tailings also reduces the need for containment structure, reduces the footprint of the tailings facility, and improves their water recovery. As I noted, they reclaim 100% of the effluent and runoff from their tailings to their mill process. They're also using the tailings here to cover old, potentially acid-generating tailings as well. So why did this tailings technology work for Canadian Malartic? This technology worked because Canadian Malartic invested time and money in the continuous improvement towards meeting their tailings solids content targets. They had flexibility in the tailings facility type because they're depositing tailings in a conventional facility. They were able to have some flexibility in the tailings solids content deposited. They already had an external water management system set up for management of the runoff and effluent from the facility. The challenges here were that it took a considerable amount of time for them to meet their thickened tailings design targets. The tailings processing methodology was not achieving the design. However, the flexibility in the tailings facility type helped mitigate that challenge. The Musselwhite Mine. The Musselwhite Mine is located 475 kilometers north of Thunder Bay, Ontario. It's an underground gold mine that produces tailings at approximately 4,500 tons per day. Similar to Canadian Malartic, this facility type deposits thickened tailings in a conventional facility and experiences a net positive water balance with a seasonal snowpack as well. The Musselwhite Mine has been in operation since 1997. Tailings property at Musselwhite Mine are along the hard rock tailings boundary. The slurry is dewatered from 50% solids content by weight to approximately 68% solids content. The deposited tailings have a concave beach slope profile. The slopes can get as high as 3 to 4% close to the spigots, decreasing to approximately 2% towards the center of the facility. Classification of these tailings is somewhere between potentially acid generating, uncertain, and non-potentially acid generating. It has a low to moderate sulfide content, up to 2%, with longer lag times to acid generation in the greater than 5-year range. Water treatment is employed at this site for water discharge to the environment as well. So why did Musselwhite Mine adopt this technology? They adopted it to increase the capacity of their existing facility by stacking the thickened tailings layers over their existing conventional tailings. This changed their closure concept from having a wet cover to a dry cover for final closure. It was more desirable from a community perspective, as this strategy allowed the mine to maintain the same footprint, minimize long-term seepage impacts, and align with future progressive reclamation plans. The benefits of this approach were reduced operational expenditure, reduced capital expenditure, and reduced operational risk when compared to a comprehensive analysis of other tailings disposal methodologies. They changed to the thickened tailings in 2010. They started operating in 1997, so Musselwhite Mine had the benefit of knowing the material properties of their tailings prior to technology implementation, and also having a large volume of material available for testing. One of the challenges for new mine projects evaluating tailings technology types is there often isn't a large volume of tailings available for proving out the technology on those specific tailings types. One of the challenges was dust management of the facility and changing the closure design approach and integrating it with the rest of the mine closure plan.
Next, we're going to talk about Greens Creek. The Greens Creek Mine and Tailings Facility is not located in Canada, although we felt it was a good example to discuss because it was mentioned in the Mount Poly Review Panel report. The Greens Creek Underground Mine and Filtered Tailings Facility is located on an island 30 kilometers southwest of Juneau, Alaska. The mine produces roughly 2,000 tons per day of tailings. However, some of the tailings are used as underground backfill, and the remaining are filtered and placed in the surface tailings facility. The tailings facility is located in a high precipitation environment, with roughly half the precipitation falling as snow. The physical classification of the Greens Creek tailings is hard rock tailings. The tailings do have the potential for metal leaching, however the lag time is very long. Now I will walk through the key elements of the Greens Creek Filtered Tailings Facility. The tailings are filtered and trucked over 10 kilometers to the tailings facility, where they are spread and compacted. The haul trucks travel on temporary rock roads within the pile. However, these roads are not trafficable during high rainfall events. The tailings are placed on a geomembrane liner for seepage control. Surface water runoff and seepage are directed to water management ponds, where it is treated prior to discharge. The pile slopes require temporary or permanent covers to control erosion. Still, there are some fines that need to be managed within the water management ponds. So why did they pick this technology for the Greens Creek mine? Filtered tailings was adopted to minimize the overall footprint. For the site that they had, the topography was such that it was easier to put in a filtered tailings pile rather than build a dam. Because there's no pond on the tailings surface, there is little potential for the tailings to be mobilized and transported during a seismic event as well. Why does this work? It works because the material properties of the tailings, they are coarse enough that the filtering is reasonable. Site conditions are conducive to the cost balance for filtered tailings. There's a low production rate, and then there's backup storage options. For example, they can send the tailings underground, and they also have a storage shed that if they need to for a couple of days. The challenges with the site is that the tailings pile does have trafficability issues during high rainfall events. There is water and erosion management that need to be done, and there's a requirement for water treatment. We'll talk about the Raglan mine. The Raglan mine is an underground nickel-copper mine located in the Nunavik region of Quebec. The mine produces roughly 4,000 tons per day of tailings. where they are filtered and placed in a filtered tailings facility. The climate is a low precipitation and cold climate. The physical classification of the Raglan mine tailings is hard rock tailings that are filtered to approximately 18 to 20% moisture content. The tailings do contain up to 8% sulfides, and they do generate acidic runoff, which requires water treatment. So why did Raglan Mine adopt filtered tailings technology? The reason is economic and water management related. The Raglan Mine is located in a region that doesn't have suitable borrow material for dam construction and also has limited water availability. Therefore, the cost-benefit trade-off between going to filtered tailings or a conventional facility was such that filtered tailings was more economic and a better way to manage the water. So why does filtered tailings work for the Raglan Mine? It works because of economics and water management considerations, as I just discussed, and it also works because of the low production rate and suitable tailings properties for the mine. The key challenges will be doing closure planning that accounts for climate change for the geochemical properties of the tailings.
We're now going to highlight some of the conclusions from the case study evaluation, as well as the information received as part of the overall tailings study. So what have we learned? The tailings physical properties need to be suitable for the technology selection, and testing prior to technology implementation should be comprehensive at the planning and trade-off stages. This testing should include both physical and chemical properties of your tailings. Achieving the design targets, the solids content, and the slopes of the facility can be challenging during startup and operations. Continuous effort and investment is required for tailings technology implementation. There needs to be some allowance for operational upsets, including backup storage, as discussed as part of the Greens Creek Mine case study. The most important point, water management cannot be avoided. You're just changing the location at which you manage most of your water. More work is required to evaluate the relationship between the geochemical properties and a dewatered facilities closure plan. We need to share more information as an industry to progress. Dewatered tailings are not widely applied in Canada. The dewater projects reviewed as part of the study have been implemented with variable success rates, ranging from quite successfully to not successfully. We still want to be here in the middle of the Venn diagram, where we're balancing our tailings characteristics and scale of the operation, evaluating the site conditions, regulatory and social environment of the site, and the available technologies and facility types applicable to both of those things. The reality is, we're sometimes still here, where we only manage to achieve an overlap of two of these key properties.
In conclusion, when selecting a tailings management strategy, you need to consider the tailings properties and site conditions, and the overall risk profile for all available alternatives. Dewatering technologies and associated facilities may provide potential benefits for some cases, but they need to be reviewed holistically and on a risk-based approach when deciding on a tailings management strategy. To date, there has not been one technology that solves all tailings management problems. There is not even one technology that is better than all the rest. There is no one-size-fits-all. Dewatering technologies are not a replacement for design, operation, and closure best practices. Therefore, a risk-based approach to tailings management should be used to select the best strategy, and best practices should be implemented in design, operation, and closure. Thank you for listening today. Lindsay and my contact details are provided on this slide, as well as the link to the MEND Tailings Study Report. After the Q&A session today, feel free to contact us if you have any further questions. On the next two slides, I've included references for all of the information presented in the presentation thus far. Thank you for attending today's webinar. I'll now pass it back to Sahar.
Thank you, Kate and Lindsay, for this excellent presentation. I will now open it up for questions. If you haven't submitted a question already, please do so now by typing your question in the Q&A box. You can also download today's presentation slides from the resource list, which is at the bottom of your screen. There is also a link there to the recording of our previous webinar, which was about the Hamada Tailings Dam. So I see we have a question already. So the question is, what's the placement methodology for placing the thickened tailings at Malartic? The photo from Malartic showed haul trucks dumping and dozers pushing material out. The photos look like rock, but we're not sure.
Hi, thank you, Erin. This is Kate. I can take that one. So Canadian Malartic thickens their tailings, and they do spigot perimeter discharge from the embankment for the waste rock pile or interior berms. So I'm not sure exactly where that picture was taken, but it looks like it was taken along the waste rock stockpile where they are depositing from that upstream face into the facility. They do often use geotextiles along the upstream face to control erosion.
Okay,
thanks,
perfect.
Sahar.
We have another question. This one says, do you have information on how well using filtered tailings technologies in northern Canadian climates? Assuming a long winter and freezing temperatures would be an operational challenge for this technology.
Yes, thank you, Carmen. There are several operations that are using filtered tailings technology in northern climates. Some of them, like Greens Creek, doesn't have quite as long winter as other sites like Raglan. However, they're both using this technology effectively right now. However, they are at smaller tonnage rates. There hasn't been large tonnage rates of filtered tailings in northern climates. We would expect there would be some operational and construction challenges with that. Good question. Thank you.
We have a question from Alyssa. She's asking on slide 19, what is ingredients in reference to?
That's in the references. Thank you for pointing that out, Alyssa. It's one of our previous slide iterations. We were actually trying to compare the tailings types to ingredients you would use in baking. Thanks for catching that.
Awesome. We have another question from Aaron. He says, he's asking, when placing tailings that need to meet certain geotechnical characteristics, how have different sites balanced the mill operational requirements with tailings geotechnical requirements?
That's a good question. So when tailings are required to be a certain percent solids or a certain moisture content, the mill needs to be able to, the processing facility needs to be able to meet that. Those are target densities. We have noted through the case studies that several of the operations had a hard time reaching those targets, so there would always have to be backup plans in place, either backup storage facilities, temporary storage, or the ability to have some flexibility in your design targets. So that's a good question of how getting design into operations. I'm not sure if I answered your question, but it is tricky balance, and there needs to be backup plans in place. Thank you.
Awesome. Lindsay, do you have any follow-up on that?
Yeah, just a note, there's been certain challenges with meeting filtered and dewatered tailings specifications in a lot of the case studies that we reviewed. And when we relate the dewatered tailings type to the facility type, it's always helpful to know that you're not going to meet specification 100% of the time. And as shown with one of our case studies, the continuous improvement plays a big role in being able to manage the dewatered tailings technology effective as part of the overall operation.
Okay, we have another question, this one from John. He's asking, what parameters do you have to consider if you are changing an existing conventional tailings pond to using thickened or paste or a combination.
So I can take that question. It's Lindsay. When converting a conventional tailings facility to thickened or paste, you'll have to consider both the geochemical and physical properties of the tailings. One of the big things is why are you wanting to make that change? So if you're interested in making the change from a storage improvement perspective or public perception, it's really about understanding the objectives to know what pieces you need to put into evaluation of the technology for your facility. In some cases, making the change from a conventional slurry tailings to thickened or high-density thickened might not change the overall outcome all that much when we're talking about things like storage, especially when considering things like subaqueous deposition of your tailings. Worked on a few facilities where we have a flooded tailings impoundment, and they're interested in moving towards high-density thickened or paste tailings. And the evaluation of whether or not that was actually going to get them the extra storage they needed really comes down to how the tailings settle out. So there's a lot of factors at play there, John, and I wish I could answer your question more specifically. But essentially, it's understanding the physical properties and if you can meet the specification in terms of the discharge from the mill, and then how that integrates with what exactly you're trying to do with the technology in the conventional facility type. Conventional facility types do offer more flexibility when moving to the different dewatering technologies, so it's a good start there, but understanding why you're making the switch is going to be important in determining what parameters you measure and what you need to know.
Okay, Kate, do you have anything to add?
I think it's also really important if you're changing the design philosophy of your tailings facility. It's really important to understand what's already been built and how you're constructing it, and making sure that the contractor or whoever's building that and the operations can understand the change in the design philosophy so that you don't end up in trouble with potential issues, geotechnical issues.
All right. Well, I don't see any other questions, and we're getting near the end of our webinar time. So if you have any other questions, please feel free to submit them now, and I will make sure to pass them along to Kate and Lindsay, and we will reply by email. You can also contact us at info@klohn.com. So thank you again for attending today's presentation. We look forward to having you join us at our next webinar. Bye for now.